And when we get here, we have to get a common denominator. So that's going to change everything in here to a squared minus x squared over a squared. Now we can manipulate this even further, moving this over here. And when you take the square root of b squared over a squared, that reduces, and you bring the b over a out front, and then you have the radical right here. All right, and that is the first step. Positive. All right, now that we've got a function to integrate, we can start setting up our integration. But before we can do that, we have to consider the area of an ellipse. And if you draw an ellipse on a graph, all you really need to do is just find one quadrant of it. So the total area of an ellipse is going to be 1/4 the area, which is also equal to the integral, which is what we're trying to do. So just balance out the equation. And now you have the area equals 4 times b over a with the integral from 0 to a of the square root of a squared minus x squared dx. Now from here, we can start setting up our table for trig substitution, because we notice that we have a radical here, and we can't really integrate the radical. There's no manipulation we can do with it. So you have your a squared, and you have your x squared. All right, so take the square root of both of those. A squared is equal to a, and x squared is equal to x. So from there, we can start making our substitutions. Our x is going to be equal to what our a is equal, which is just a. And by using our table for trig substitution, we know that a minus x is going to be x equals a sine theta. From there, we just integrate that, or differentiate that. Then you're left with a cosine theta d theta. Now from there, we can start making our substitutions. Where? Hang on. So now that we have our table set up, we can easily start doing our substitutions to get this radical to get the hell out of here. So we have the area of an ellipse is equal to 4 b over a integrated from 0 to a. And now under the radical, we start making our substitutions. So we still have a squared, because that's just a constant. But every value of x, we plug in this, which is just 1. Just plug in a sine theta squared. Now we also have to change the d theta with respect to what we're integrating to. We're trying to get these in a trig. Trigonometric, not identities, trigonometric. So like we did with x, we have to plug in what we found for dx to get everything in terms of theta. So that's given as a cosine theta d theta. Now here we just we square this whole thing inside. and we're left with a squared minus a squared times sine squared theta times a cosine theta d theta. And after that, right here, you can just pull out a squared, and we're left with 1 sine squared theta in here. And now from here, we know that this is Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. So always got to manipulate it around, and we have this is equal to sine squared. Oh wait, damn it, I put backwards. I'll edit it later. Total sine squared theta is equal to 1 minus sine squared theta. So go down here, and we have 4 times b over a, integrating from 0 to a of the square root, a times the square root of, pause it? Good? Mm-hmm. Alright, so once we make this substitution right here, we also have to take care of this a squared. So that's just going to leave us with a on the outside, and we're going to have cosine squared theta on the inside of the radical, which we can easily get rid of. And now we're left with 4 times b over a times the integral from 0 to a of a cosine theta times a cosine theta d theta. Now we have an a down here, we can cancel that out, which will give us 4ab times the integral from 0 to a of cosine squared theta d theta. Now here we have to change the limits of integration into something that we can attribute to an actual area under of a curve. Because right now this is just a placeholder for a constant. So to do that, change the limits of integration. We take our lower limit and set it equal to our substitution, which is a sine theta. Divide by a on both sides, and we're left with sine theta equals 0, which is the angle that gives us, when we take the inverse sine, will just be 0. So that's our lower limit. Now to find our upper limit, we set a equal to the substitution, which is a sine theta. We do the same thing. Divide by a, left on with 1 on this side. And the angle we get when sine is 1 is going to be pi over 2. So now we have our limits of integration. We can start actually integrating and solve from there. So we have the area is equal to 4ab times the integral from 0 to pi halves of cosine squared theta, d theta. Now we can't integrate this directly, but we can use a half angle identity or pi reducing formula. Which is cosine squared theta equals 1/2 times 1 plus cosine 2 theta. So we just take that and put that in the integration. So we have a equals 4 times a times b times the integral from 0 to pi halves times, or the integrand is going to be 1/2 1 plus cosine 2 theta d theta. Now that 1/2 will cancel out the 4, and we're just left with 2 right there, 2ab, and we can easily integrate that, which is just going to be theta, and it's just a common integration. You know that for u substitution, it's going to be 1/2 sine 2 theta. So put that all in there. 2ab times theta plus 1/2 sine 2 theta. From pi halves, 0 to pi halves. From there, we just use the evaluation theorem. The upper minus the lower. So we have pi halves plus 1/2 sine 2 times pi halves. And that's minus everything plugging in 0 to where theta is, which is just going to give us, 0. Now here, 2's cancel out, and then we're left with sine pi, which is going to be 0. So this whole thing is just going to be 0, and we're left with 2 times a times b times pi halves, which is just going to be pi times a times b.